Alright, in this video we will be going over an example for the derivation of the equations for the step response of a second order RLC circuit. We're specifically doing a series RLC circuit where we have a resistor in series with an inductor and a capacitor and a switch that closes at time t equals 0 with a voltage source Vs, and we are going to be asked to find the equation for the current through the circuit, I of t, as a function of time. Now, this is just going to be one example of one possible configuration, but the procedure you are going to use to solve a problem like this will be similar. If you've seen the previous videos in this series, we did this for an RC circuit and an RL circuit, where we were solving for either V out or the current as a function of time for a similar step input. And I talked about how you could swap these around, have the capacitor or the inductor first and then the resistor, and be asked to solve for either the voltage over one component or the current through a component. And the general procedure is going to be the same idea here, except now we have a second order circuit, meaning I have two independent energy storage elements. So here I only had one energy storage element per circuit, either a capacitor or an inductor. And when I say independent, that means it's not something just like two capacitors in parallel where I could combine them to a single capacitor and they're not, the voltage across them is going to be the same, so they're not independent. Here I have two separate independent energy storage elements, making this a second order circuit. Now, as we did with first order circuits, we're going to have a bit of a crash course differential equations review to make this a little easier. So again, this is covered in the earlier videos in this playlist. If I have a differential equation of this form, tau dx dt plus x of t equals k, some constant times some forcing function, then for a step response or a constant forcing function, the time response of that system is going to be x of t equals the initial condition, x of 0, minus x of infinity, the final condition or steady state condition, e to the negative t over tau, where tau is that time constant from this form of the equation, plus the final or steady state condition. So that is first order. We are going to have a similar setup for second order, where if we can get a differential equation in a certain canonical form, then we're going to know the solution to it. And by know, I mean we are just taking it for granted because this isn't a differential equations course, so I'm not going through the steps to actually get from there to there in this video. So for a second order linear differential equation, we have 1 over omega n squared, and I'll talk about what all these variables mean in a minute, d squared x dt squared plus 2 zeta over omega n times dx dt plus x of t equals, again, some constant times a forcing function f of t. So that is for second order. And my variables here, omega n is the natural frequency. This equation on these terms might look familiar if you have taken a system dynamics class, where again you could spend weeks on second order systems like this. We're just kind of covering it in one video here. Zeta is the damping ratio, and K is the gain, as it is for the first order system. F is the forcing function. So again, this is all for a second order system. And we are going to have the solution to that equation, x of t equals alpha 1 e to the s1 t plus alpha 2 e to the s2 t plus x of infinity, the steady state or final solution, where s1 and s2 are equal to negative zeta, the damping ratio, times the natural frequency, plus or minus omega n square root zeta squared minus 1. So that was a lot, but again, remember the procedure we're going to go through in the rest of this video is we're going to analyze this circuit to get a differential equation in this form. Once we have it in this form, we know that this is the solution. The solution is just a little more complicated with some extra terms S1 and S2 in there, which, to be clear, are also constants. They are just functions of that damping ratio and natural frequency. Alpha 1 and alpha 2 are also constants that we are going to need to solve for based on the initial conditions for this equation, and we'll go through that. So, and a quick overview of, again, some stuff you would see more in a system dynamics class that we're not going to go into a ton of detail here. Depending on the value for this damping ratio, you're going to see different behaviors in the system. So if zeta is greater than 1, we call that overdamped. In that case, both S1 and S2 are real. S1 does not equal S2, and the solution is what we have written above. Okay. If it is exactly equal to 1, we call that critically damped. If I can spell. Here we have S1 equals S2 equals negative omega n. And the solution here is alpha 1 e to the negative omega n t plus alpha 2 t e to the negative omega n t plus x of infinity. Finally, we have underdamped, zeta, greater than 0, less than 1. Here we have S1 is equal to the complex conjugate of S2. And then finally, I'm kind of running out of space at the bottom here. Zeta equals 0. We have undamped, where S1 equals negative I. Remember, this is the square root of negative 1, not current. Omega n t, and S2 equals I omega n t. And the solution is x of t equals alpha cos omega n t plus phi. So you notice in there is no decaying exponential. Since this is undamped, there's no friction. That one is just going to oscillate forever. Whereas anything with damping, eventually the friction in a mechanical system or the resistance in an electrical system is eventually going to damp out the response of one of those systems. So that's kind of the intuitive way to think about what this damping ratio means, is how much friction or how much resistance is there. So in a totally undamped system with no friction or no resistance, it's going to oscillate forever because there's nothing to dissipate energy or slow it down. But in all other cases, either overdamped or critically damped or underdamped, it's still going to stop eventually. Okay, great. There's our differential equations review. If you were skipping ahead from earlier in the video, this is where you want to pick up. Let's go on to a new slide. So we're going to redraw our circuit. We have our switch closing at times t equals 0. Then we have our resistor R, our inductor L, and our capacitor C. And we want to solve for the current, not voltage, through this circuit. So we are going to find the initial conditions and the final conditions for our circuit. So the initial conditions are immediately after the switch closes. The final conditions are after the switch has been closed for a long time, because we know, just like for the first order circuit analysis, we're going to need these later. So RLC. Immediately after the switch is closed, we can apply our continuity rules, which we went over for inductors and capacitors earlier. There are certain variables or parameters that must be continuous for each of these. We know that for a capacitor, the voltage across a capacitor must be continuous, and for an inductor, the current through an inductor must be continuous. So if I know that initially my circuit is sitting here, the current has to be 0 because the switch is open. So before the switch is closed, the current is 0. Then immediately after the switch is closed, I know the current through an inductor must be continuous. So the current at time t equals 0 after the switch is closed must also be 0. I know that initially, if there's no voltage over any of these components, then here the voltage across the capacitor must also be 0 the moment the switch closed, because the voltage across the capacitor here was 0. Switch closes, voltage across the capacitor must remain 0 in the moment, that instant right after the switch closes. And again, we go over these more in previous videos talking about inductors and capacitors in this playlist. Then in steady state, for my final condition, so here's t equals 0 right after the switch closes. Here's t goes to infinity after the switch has been closed for a very long time. We also talked about the steady state conditions where an inductor just acts like a short circuit in steady state, and a capacitor acts like an open circuit in steady state. So I'm just going to replace my capacitor with an open circuit. And again, I'm not going to go over the reasons for those in this video. You're going to need to go back and rewatch the inductor and capacitor videos for the kind of explanation behind that. So I know that here in steady state, well, now I have an open circuit, so my current as time approaches infinity also has to be 0. And you might think, well, wait a minute, if the initial condition current is 0 and the final condition current is 0, well, then how does the current ever do anything? If I'm going to draw a graph of current versus time and my initial and final conditions are both 0, then is my graph just going to look like this? Because when we did first order circuits, we had some initial condition and final condition, and we got this time constant response where it would asymptotically approach the final condition. The difference is that a second order system can oscillate. So if we have the same initial and final condition, that is perfectly possible because my response might look something like this, where I kind of have some initial oscillations that, again, because I have some resistance in my system, are eventually going to damp out, and I can return back to that 0 initial condition. It doesn't have to be the same. I could have, say, something with an initial condition here and a final condition here where my response looks like this. And again, this is something you're going to see much more of in a system dynamics course where you talk about rise time and overshoot and settling time and all of those things. Not going to go into a ton of detail here in this video because, again, you'll get a much better treatment of that in a system dynamics course. But the rough analogy or way to think about this is that the point of learning about these RLC circuits is that electrical systems can oscillate just like mechanical systems. So if you think of this as, for example, pinging, you have a beam that's fixed on one end and you ping the end of the beam with a force, it's going to oscillate for a bit, but eventually reach a new steady state deflected position where it's no longer vibrating because friction is going to dissipate the oscillations. And if you make a graph of, say, the velocity of the tip of that beam as opposed to the position, then it's going to look like what we have here, where the velocity is going to oscillate and eventually return back to 0. If you make a graph of the position, then it's going to return to some separate final condition value that is not necessarily equal to the initial value, but same idea here. You have a mechanical system that you would model as a spring mass damper with some mass connected to a spring and damper, so it has both a restoring element and friction. Then mathematically, what you get is the same as what we showed in the previous slide. It's just in the mechanical domain instead of the electrical domain. So again, you'll get a lot more of this in a system dynamics course, but that's the idea. In the rest of this video, we are going to analyze this in the electrical domain with an RLC circuit. Okay, so all that work was to find our initial and final conditions. Now let's try to get that second order differential equation in this form so we can find the solution in this form. The same approach, or we're going to use the same approach we did for the first order circuit by starting out and writing down all the equations we know for our different electrical elements. So we know the Ohm's law, voltage across the resistor is equal to the current through the resistor times the resistance. For an inductor, we have the voltage across an inductor is equal to the inductance times di dt, the derivative of the current. And for a capacitor, we have that the current through the capacitor is equal to the capacitance times the derivative of the voltage across the capacitor. Great. We also know Kirchhoff's voltage law, voltages add in series, and Kirchhoff's current law, currents are the same in series or add in parallel, however you want to phrase them. So I'm going to rewrite our equation from the previous slide so I don't have to keep flipping back and forth. We want an equation of this form: 1 over omega n squared d squared I, second derivative of I, because that's what we are trying to solve for, plus 2 zeta omega n di dt plus I equals some constant times f of t. Okay? So I'm going to start by applying KVL to the circuit and see where that gets me. So I have these three elements in series, so I know their voltages, the voltage across the resistor, plus the voltage across the capacitor, across the inductor, plus the voltage across the capacitor must equal the source voltage. Actually, sorry, I'm applying that here once the switch is closed. And I'm now going to plug in my different equations, because remember, I want a differential equation in terms of I, not in terms of voltages. And since these three elements are all in series, Kirchhoff's current law, I know the current through them must be the same. So plugging in Ohm's law for the resistor voltage, I have IR, plus plugging in the inductor equation for the inductor voltage, I have L di dt. So you can see I'm starting to get some derivatives, a differential equation kind of the form I want. But then for my capacitor equation here, well, I'm going to have to integrate this, because here I have a V, not a dV dt. So if I integrate this equation and move, I'm not going to work through the algebra, but move the C over to solve for voltage, I get 1 over C times the integral of I dt, and that's all going to be equal to Vs. Okay, so I almost have an equation in the form I want, but not quite, because this equation has a second derivative, and I just have a first derivative and an integral, but I can differentiate this entire equation to get the form I want. So it'll get rid of the derivative and give me a second derivative. So I'm going to do that, move up here, take the derivative of that entire equation, and rearrange terms a bit. I'm going to get R times di dt. So that was the first term there. Took the derivative of that. R is a constant. I is my variable. So I just moved the R out front. Plus L times the second derivative of I, d squared I, dt squared. That was this term here. Plus 1 over C times I. So that was this term's here. Taking the derivative, canceled out the integral. I still have the 1 over C constant out front. And all of that equals 0, because Vs is a constant, so taking the derivative gives me 0. So again, that was just taking the derivative of this whole equation so I can get that second order derivative and have it in this form. But you can see that I do not have a coefficient on my I term here, so I need to rearrange things a bit, and I can do that by multiplying the whole equation by C to cancel out the C, the 1 over C coefficient in front of my I. So, and then I'm also going to flip the terms around, so my second order derivative is first. So doing all of that gives me LC d squared I dt squared. Again, that was multiplying this term by C and moving it to the front, plus RC di dt. That was multiplying this term by the C and moving it here, plus I of t. That was just multiplying this term by the C to cancel out the 1 over C, equals 0. Okay, great. Now I have, I'm going to switch to a different color, this equation in this form where I have my constant LC is equal to 1 over omega n squared. My constant RC is equal to 2 zeta over omega n. And then I don't have a constant here. And from my previous slide, I know that my solution, I of t, is going to be equal to alpha 1 e to the s1 times t plus alpha 2 e to the s2 times t plus I of infinity. And just writing my equations for s down again, that is s1 comma 2 equals negative zeta omega n plus or minus omega n square root zeta squared minus 1. So give me a second to jot that down again so we have it all on this slide. Oh, doesn't like it when I write towards the bottom. Try and cram it in over in the corner here. s1 comma 2 equals negative zeta omega n plus or minus omega n. Oh, I'm going to run out of room and run this on to the next line. Times the square root of zeta squared minus 1. Okay. Looking at all of that, you might say, well, great, I don't actually know omega n squared, or I don't know omega n or zeta yet. I just have this coefficient LC and RC. But here, L and C are constants, and then my only unknown is omega n. So let's actually move to the next slide because this is getting a little too crowded. So I know that 1 over omega n squared equals LC. Okay, so I can rearrange that to solve for omega n since that is my only unknown here. And then I know that 2 zeta over omega n, 2 zeta over omega n equals RC. But once I have used this equation to solve for the natural frequency, then R and C are constants, so my damping ratio is my only remaining unknown in this equation. So I can use those to solve for both omega n and the damping ratio, because again, I know R, L, and C, those are constants for the problem. And then once I know zeta and omega n, I can solve for S1, negative zeta, omega n plus omega n, square root zeta squared minus 1, and S2, negative zeta, omega n minus omega n, square root zeta squared minus 1. Great. So writing down my equation yet again, so we don't have to keep flipping back to previous slides. I of t equals alpha 1 e to the S1 t plus alpha 2 e to the S2 t plus I of infinity. Great. I have my final condition. We found that a few slides ago. I of infinity is equal to 0. I have S1 and S2 because I have S1 and S2 here because I know zeta and omega n. I know zeta and omega n because I know RL and C, so I can solve for them from these equations. Great. It looks like I have almost everything in this equation, except I don't know alpha 1 and alpha 2 yet. I have to solve for these constants somehow before I can have the complete solution. And you might say, wait a minute, that's a problem because we know our initial and final conditions. We found that earlier. We know I of 0 and we know I of infinity, but we still only have one equation and 2 unknowns here. I don't know alpha 1 and alpha 2. One equation, 2 unknowns. How do I solve for alpha 1 and alpha 2? For a second order system, we need a second initial condition so we can have 2 equations and 2 unknowns. So I could go ahead and plug in t equals 0 for this, right? I could say I of 0 equals alpha 1 e to the S1 times 0 plus alpha 2 e to the S2 times 0. And I know I of 0, we solved for that a few slides ago. That is also equal to, I'm going to write that down over here. I of 0 equals 0, and I of infinity equals 0. We solved for those earlier, so I know that equals 0. But again, that's one equation, one equation, 2 unknowns. If I want a second equation, I can find the initial condition for di dt of t equals 0. Take the derivative of this entire equation, then I have 2 equations and 2 unknowns. So we're going to do that next. So simplifying this a bit, e to the 0 is just 1. So for our general first initial condition, we're going to have I of 0 equals just alpha 1 plus alpha 2. In the example I gave for this problem, I of 0 equals 0, but that might not be the case for the problem you're given. So keep it more generally here. I of 0 equals alpha 1 plus alpha 2. We're also going to take the derivative of this equation, ddt of this whole thing, and that's going to give us di dt of t equals 0 equals alpha 1 s1 e to the s1t plus alpha 2 s2 e to the s2t, and then this term's a constant, so that drops out. So plugging in t equals 0 for this, di dt t equals 0 equals alpha 1 s1, which again s is, remember, a constant that we know from this whole chain working backwards up here, plus alpha 2 s2, because then this term just becomes 1 when you plug in t equals 0. So in general, once you have solved for both your initial condition and the derivative of the initial condition, or the initial condition for the derivative, Then you have two equations, two unknowns, where you can solve for alpha 1 and alpha 2, but you have to know these initial conditions. And remember, we found the initial condition for our current by using our continuity rule and knowing that the current through the inductor had to be 0 immediately after the switch closed, because the current was 0 before that. Current through an inductor has to be continuous. But we need an initial condition for the derivative of the current, and we can find that by looking at our KVL application again, where we had the three voltages summed equals the source voltage. And remember that, again, from continuity, we know that the voltage across the capacitor has to be 0, because voltage across the capacitor is continuous, so if it's 0 before the switch closes, it's 0 after the switch closes. We also know that the voltage across the resistor is going to be 0 initially, because if the current is 0 initially, the voltage across a resistor is the current times the resistance. So if the current is 0, the voltage is 0. So the voltage across the resistor is 0. That leaves us with the initial condition at time t equals 0, VL equals Vs. But what's the equation for an inductor? L di dt. So we have L di dt equals Vs. Remember, all of this is at time t equals 0. And this is what we're after. We want the derivative of the current at time t equals 0. So to get that, all we have to do is divide both sides by L. And we get di dt at times t equals 0 equals Vs over L. And there we go. There is our second initial condition. That is specific to this problem. Again, remember, in this specific case for the example I'm giving, we had the initial condition. There's our first initial condition, the current at 0 equals 0, and the derivative of the current at time equals 0 equals Vs over L. That is for this specific circuit configuration and the problem I asked you to solve for the current. That is not always true, but in general, the two equations you're going to want to solve for alpha 1 and alpha 2 are going to be this one and this one if you're asked to solve for the current. So, kind of a recap there, you have this entire equation which gives you the response you're looking for, current as a function of time, but this equation has a whole bunch of constants in it, so you have to figure out those constants in order to fully solve this equation. I'm doing everything symbolically here, but if you're given a problem with numbers in it and you need the numbers, you can ultimately plug in. So you need to find the steady, going through these one at a time. You need to find the final or steady state condition by applying your steady state rules for resistors and capacitors. There's part one. You then need to find S1 and S2. In order to find S1 and S2, you need to find the damping ratio zeta and the natural frequency omega n. In order to find the damping ratio and the natural frequency, you need to find the second order differential equation of this form, where in this problem, it just so happened that these coefficients worked out to be equal to LC and RC, which then allowed me to solve for omega n and then zeta. But that is not always going to be true depending on your circuit configuration. These could wind up being, or you have multiple capacitors, resistors, inductors, and so on. This could wind up being different, but that is the general procedure you're going to follow. And then finally, so that gets you the final condition, S1 and S2, but you still need these two constants, alpha 1 and alpha 2. To find those, you need your initial condition and the derivative of your initial condition. So a lot of things you need, but you can systematically work through it, giving the order I gave you there, and ultimately that will then give you this equation with all of the constants you need.